My name is Beattie. I am a software developer, a systems architect. I am also a qualified scientist, as you will discover over the course of the talk I'm going to give you this afternoon. Because what I'm going to talk to you about today is science and software development. They are interesting disciplines. Has anyone in here studied computer science? Yeah. Did you do any experiments in the course of becoming a qualified computer scientist? Because the premise behind this talk today is to take a look at some of the ideas that the scientific community has used for a long, long time to further understanding of phenomena and unfamiliar systems, to make sense of data and analyze things, and look at how we as software developers might be able to apply some of that to what we do. The relationship between computers and science is complicated, and it's one that has inverted quite dramatically. If you go back a few decades, to do any kind of computing at all, you would actually have to do quite a lot of hands-on science. There was also electronics, physics, just to get early computers to boot, to work. Computing was very, very much, the idea of solving a problem by running a computer program, it would have to be a very, very sophisticated and important problem to be able to justify the scientific resources necessary to get computer time in order to do it. People would write programs on paper because computer time was so expensive that waiting for somebody to type was unthinkable. So you'd write it on paper, you'd punch it on cards, you'd in some cases send it off by post, and you'd get a report back saying missing semicolon at line 26 or whatever the problem was. Nowadays that relationship has almost completely inverted, and we use computers now routinely to simulate scientific phenomenon. Computing is a big part of an awful lot of scientific research. But what we're going to do today is to talk about something called the scientific method and how I think that can be applied to improving the development of software systems. As I said, I'm a qualified scientist. I have a Bachelor of Science in Computer Science with Image and Multimedia Systems from the University of Southampton. I was there for 3 years. I did no experiments. What I did was I learned about things like the red-black tree and data structures and algorithms and databases. And lots and lots of stuff was presented as, this is a fait accompli, this is a fait accompli, this is how you do this, this is how you do this. The bias, I had classmates or friends who were in chemistry and biology classes who would do labs. They would, on a Wednesday afternoon, they would actually do experiments. Sometimes they would do experiments where they didn't know what was going to happen, and they would actually be investigating something. In the computer science building, we had labs, but they were full of Linux machines, and we used them to check email and write scheme programs and this kind of thing. And there was an interesting contrast that I noticed, because during my time at university, I also had a holiday job working for Arup, who are an engineering company. They built this, and they built the Urson Bridge and the Pompidou Center and all sorts of things. I built none of these. My job was installing Windows 3.1 and WordPerfect. But the contrast between the conversations that you would overhear, we love metaphors in software. We talk about, my job title is architect. That was designed by an architect. I could not design one of those, We talk about build pipelines. We talk about engineering. We borrow all of these metaphors from the construction industry. But it doesn't really add up, because there's one sort of fundamental difference. I want you to imagine that you're starting a new company, and you have some staff, and those staff need a way to be able to write letters to your customers. So you go into a computer store and you say, I need a software program to write letters. And they say, okay, well, first of all, we're going to need to do a requirements gathering exercise with you. We'll send a team. They'll work with you for 6 to 8 weeks. We'll come up with some ideas, work out what it is that you actually need. Then we're going to come up with a tender. We will put that tender out. There are maybe 15 companies in this part of the world who make word processors. I'm sure one of them will be able to help you. The whole thing will probably cost a couple of £1 million. They should be able to get you a word processor built within 18 months. It sounds crazy. If you want an office for your new company, this is exactly what you do. If you want a word processor, you go into a shop and you go, can you sell me a copy? Or you go onto Microsoft.com and you put in a credit card number and you download a copy. And the contrast here, it is easy to replicate bits of bits, streams of bits, data. Once you've solved the problem once, it's trivial. Now, there are all sorts of endeavors where this is not the case. Engineers who build bridges, once you've built a bridge, you cannot copy and paste it, or download it, or get bridges off BitTorrent or whatever you do, and just paste them in wherever you need them. You have to build another one, starting from nowhere, nothing. Furniture. They make a chair, the next day they make another chair, the next day they make another chair. Bicycles, musical instruments, artifacts. We have this word in English, this word is masterpiece. Now, a masterpiece colloquially means something that is incredibly intricate and well executed. It's an artifact, it's a work of art. What masterpiece originally meant, somebody would apprentice. They would start at the very bottom and they would make a chair. And they'd probably get it wrong and it would fall apart. And they'd come back and they'd make another one and another one. And over years, we're talking here about people who would develop these craft and skills over a lifetime. One day they would go, I think I'm ready. I think I'm ready now to produce the best chair I will ever produce, to prove that I am now a master carpenter, or a master luthier, or a master builder. Because over the course of their apprenticeship, they got to do the same thing over and over and over again. Now, I want you to imagine Monday morning, or whenever you start your working week, you log in, or you walk into the office, or you report for duty, and someone says, we've had a bit of a problem. All the code is gone. It's gone. All the hard drives are gone, and the backups are gone, and the tapes have been wiped, and GitHub's been taken offline by attackers. Everything you were working on has disappeared. And so you go to your client, or your customer, or your boss, you say, what do you want us to do? And they say, start again, Don't worry, here's a laptop, Visual Studio, off you go. Whatever you were working on, we need to start it again. So you do. You sit down, you think, okay, where were we? Right, we're building a little marketing website for a local, bakery. And so you start working on it, putting bits together. Pretty good week. You come in the next week, they're like, it happened again. We don't know what keeps happening at the weekend, but someone's coming in and removing all of our code. And you say, what do I do? And they say, start again. And this keeps happening. After 3 months, how good do you think you would be at building a marketing website for a local bakery? You've started from scratch every Monday, for 6 months. You've got to go back to square one and start the whole thing all over again. Anyone ever play Super Mario? Yeah. Super Mario had no save game, did it? You started, you plugged the cartridge in, and you were there at the beginning of the first level of the first world. And you started playing until you died. And when you died, you went back to the beginning. And by the time you got to the end, you could probably do the first half of that game, with your eyes closed. You do it in your sleep. Because you did it over and over and over until the point where you no longer made mistakes. And this is why I think, some of these ideas are applicable to software. Because in software, if we have solved a problem, if we have come across a problem before and we have created some code in order to solve that problem, the code still exists, and in most cases, the cost of reuse is, I hesitate to say zero, for reasons that we'll go over shortly, but it is much, much easier to take some code that already exists and apply that to the problem at hand than it is to go, you know what, I need to put this list in alphabetical order. Oh, well, time to write a sorting algorithm. I wrote 6 of those last week and 3 the week before, and they're all the same algorithm, so I'm getting really good at it. That's not what we do, We put together components. We take components and libraries and modules and functions. All of the problems that we know how to solve, it is trivial to reuse the solution that already exists. And this has a corollary which I think is dangerous and interesting and very important to bear in mind, because once you get to the point where you're like, I've looked on the web, there's nothing on Stack Overflow, there is nothing on GitHub, I can't find anything on the Node Package Manager or NuGet, there's nothing in the standard library, I'm going to write some code. The fact that you are writing code means you are doing something that has not been done before. And in some cases, this is really cutting-edge stuff. You're building new optimization algorithms for heuristic encoding of audio. In some cases, this is just our accounts team have got this package, and our sales team have got this package, and as much as we wish it were not the case, apparently nobody in the history of the world has ever connected these 2 packages together before. And so there are these gaps, and these gaps are where you have no idea what you're doing. There's no prior art. There is no off-the-shelf solution. There are things that call themselves best practice, but it's dubious how much of a benefit that really is. And so we often find ourselves in these situations where we are dealing with an unknown situation, something we have to analyze, we have to study, we have to try and work out how it all fits together. The computer industry is not terribly experienced at this because it is not a very old industry. But for centuries, human beings have been studying these unfamiliar phenomena and unfamiliar data sets using something called the scientific method, which is a toolbox, it's a framework, it's a technique for making sense of and understanding something new, something unfamiliar. And it goes like this, and we're going to see this a lot today. You start with an observation. Whatever it is that you are working on, the system that you're looking at, find out what you can about it, watch it, see it in action. If somebody else has worked on it, read what they wrote. If you can look up source code for it, look up the source code. Find out as much as you can. Sooner or later, somebody is going to come up with a question. Hey, can we get this system to talk to that system? Hey, there's a problem with performance. Can you look into it? And these tend to be open-ended questions. And so the next step then, based on your observation, formulate a hypothesis. There's a problem with the database. Okay, I think, based on my observation, that the problem is because this column needs an index. A statement that you can determine to be true or false about the system or the data that you are working with. Because once you have a hypothesis, you can make a prediction. If I add an index to this column, we are going to see a 90% reduction in the execution time for this query. You design an experiment. Whatever it is that you're predicting, how can you said, okay, I think if I do X, then Y is going to happen. Do X. Find a way of doing it. Sometimes this is trivial and you can do hundreds of these in a day. Sometimes this is an entire life's work. But hypothesis, prediction, experiment. When the experiment is finished, you have data. Or maybe you have no data. Maybe the experiment yielded nothing. The absence of data is still a data point. It is still something that is worth analyzing and thinking, why did I get nothing? What mistake might I have made? What were the flaws in my prediction? Communication. You've discovered something. Publish it. Share it. Make sure people know about it. Share it as what it is that you have found so that the next person to go around the cycle, when they get to the observation step here, they can pick up the things that you have communicated and not have to repeat the process that you've been through. Now, there's a shortcut in this, an optimization which often happens, which is that when you get to the analysis stage, you'll go, hang on a second, my hypothesis wasn't quite right. I missed something. There was a detail here that wasn't apparent until I went in and looked at these data. And so you go back to the hypothesis step, and you go around the circle again. Now, I'm going to show you an example now, one of the earliest and most famous experiments that's ever been done. Anyone in here got kids? Or anyone here know kids? Yeah. Kids are brilliant scientists, except they're not allowed to play with chemicals or burn things. But kids are curious, and kids are like, Daddy, why is the sky blue? Daddy, how does the sun work? Daddy, why does it rain? Daddy, how do rainbows work? Now, rainbows are older than humankind. They've been around forever. People since the dawn of humanity have looked up and seen rainbows and come up with hypotheses about what these rainbows might be. Some people believed that it was the bow that the thunder god used to launch thunderbolts at the earth, because it's kind of bow-shaped. Some people said it was the cloak of the sun god. Some people said that it was a rainbow bridge that connected Earth to Valhalla. These are all hypotheses. These are people looking at something and going, I got an idea about what that might be, where it comes from. But the hypothesis we're interested in is this guy, Newton, Isaac Newton, who, despite actually being a deeply spiritual man, did not think that rainbows had anything to do with gods. He had a theory about the nature of light. Now, when you research the sort of history of science, you will often find that someone will write something like, oh, everybody believed X at the time, and then there will be, citation needed because they don't actually back this up. And there were, as far as we can tell, there were various theories about the nature of light prior to the work that Newton did. One of which was that all light was fundamentally white, and if you wanted red light, you took white light and you added some red to it. And that's what happened when sunlight would bounce off a red chair or a red rose or something, just the way it worked with paint. Newton had a different hypothesis. And thanks to the wonder of communication and the wonder of Google Books, we can read exactly what his hypothesis was, because his original manifesto on optics is online, where you can go to this URL and you can look at it. And his hypothesis was, I think the light from the sun consists of rays which are differently refrangible, which is this lovely archaic word for refracting. And he said that lights which differ in color differ also in degrees of refrangibility. He's basically saying, I think white sunlight is actually made up of all of these different colors all mixed in together, and I think if we were to refract them, we'd see they come out at different angles. So, observation, Newton looks up, rainbow. Hypothesis, prediction, differ also in degrees of refrangibility. This is his prediction, you know. Experiment. The proof by experiments. In a very dark chamber at a round hole about 1/3 part of an inch broad, made in the shut of a window, I placed a glass prism whereby the beam of the sun's light which came in might be refracted upwards towards the opposite wall. Now I have a prism, and I don't have a window shutter, but I do have a flashlight, because the important thing about communication in science is it means that anybody who comes across your writing, your research, does not have to trust you. They can try exactly the same thing you tried, and they can verify whether it works. Because the thing about Newton, there's no photographs or anything of his experiment, because cameras hadn't been invented yet, because this was the first research into optics anyone ever did. So what we can do is we can take a flashlight, and we can take a prism, and if we are lucky, we can reproduce exactly what Newton saw. So yeah, the people at the front will tell you this is a stunning visual spectacle. It's overwhelming. That's exactly what he did. He took a beam of white light, he shot it through a prism, and it came out in this, what we know now as the rainbow, the electromagnetic spectrum. He communicated his results. He communicated them so well that this became absolutely iconic. You know, this image of the rainbow spectrum pops up in culture all over the place. You've seen this. I showed Rob Connery this earlier, and he said, you can't show that without Nyan Cat. So Rob, this one's for you. What Newton actually did was he published a treatise. First, he went to the Royal Society in London. He said, look, I did this amazing experiment with this glass prism that I bought at the fair and this ray of sunlight, and I made a rainbow. And then he published his treatise on optics. And this, you know, with a couple of updates to language and content and things, is still basically the backbone of physics curricula on optics. You know, I learned stuff at school and at sixth form college, which are basically straight out of the stuff Newton wrote centuries ago. And because he did it, because he communicated it, we haven't had to do it again. We can build on top. There is this lovely quote Newton wrote to Robert Hooke one day, and he said, if I have seen further than others, it's because I have stood on the shoulders of giants. There is a tangential quote from the father of Visual Basic, which is, if scientists are standing on the shoulders of giants, the software industry is midgets standing on the toes of other midgets. But, you know, he communicated these findings, and we now, all of us have, you know, cameras on our phones in our pockets. We have color displays. We have SLR cameras. We have the Hubble Space Telescope. All this stuff is because people didn't have to start from square one. They could pick up where Newton left off, and they could build on what he had published. And generation upon generation is built on this. So how can we apply that sort of, you know, discipline and good stuff to software? So we're selling stuff, and we have a checkout. And we've just launched a new checkout for our, you know, e-commerce system where we're selling luggage online. And for some reason, observation, we're seeing lots of abandoned shopping carts. People are getting on, they're putting stuff in their cart, and then for whatever reason, they're going away, they're disappearing, they're not getting any money. So we have a meeting. And it's one of those meetings because Dave is in the meeting, and Dave doesn't like the people who built the new checkout. And Dave has kicked his heels in, and Dave is absolutely adamant that, no, the reason we're seeing abandoned things is because the design is rubbish. People don't like it. They're getting to the checkout system, and they're going, I'm not giving these people my money. You ever had one of those meetings where that then degenerates into like an argument where it's like no one is bringing any new information to this? It's just two people hoping the other one is going to run out of patience and they're going to win because they're still shouting. I don't want to have those kinds of discussions anymore. I want to do science. So what we're going to do is we're going to take this observation and we're going to say, okay, Dave, we think maybe you are correct. You have this idea that people are dumping the shopping cart because they don't like the design. That's a hypothesis. So, observation, shopping carts are getting abandoned. Hypothesis, they are getting abandoned because people do not like the design. Prediction, if we show people alternative designs, this one will, play badly against alternatives. We will see a sort of pronounced drop-off in the number of people who convert an order using this shopping cart versus the previous design. How would you design an experiment to go in and validate this? There's an idea we have in software, something called A/B testing. Come across this concept? You launch two of something, and one bunch of people sees one of them, and one bunch of people sees the other one, and you track how those groups of users behave. It's hard to do. It's hard to do if you have small user groups. It's hard to do if you have a code base that doesn't support it, but it is also an incredibly valuable technique for better understanding the way people are using the systems you're creating. So we design an experiment. When people arrive on our website, we are going to use some mechanism to split them equally into two groups, A and B. And group A are all going to get the old shopping cart that hasn't been redesigned, and group B are all going to get the new one. Pretty simple, right? We conduct the experiment. Now, if you switch it on for half an hour, I read anecdotally somewhere, if Amazon want to try a new feature on 1,000 people, they switch it on for 17 seconds. Most of us do not have this luxury. So when you are conducting your experiment, gathering your data, do it over a period of time that you get enough data that it's actually representative. Run it for a couple of weeks. So you get the people who are shopping online at work during their lunch hour, you get the people who are shopping online late at night, you get the people who do shopping over the weekend. Let it run for a while. Let it run so you have a statistically significant volume of data to analyze. Then analyze the data. And so at this point, we've got all of these checkout logs and all this data from all these people. We communicate it. We have another meeting. We're like, we didn't see any correlation whatsoever. People going through the old checkout system, 41% of them never completed the transaction. People going through the new checkout system, 38% of them never completed the transaction. To within a degree of experimental error, we don't think there's any correlation there. And that's when someone in the meeting pops up and goes, hey, while I was looking through all this data, I noticed something. I noticed that a lot of the people who weren't completing their transactions are using Firefox. So I now have, bang, a new hypothesis. I think there might be a problem that means people who are using Mozilla Firefox can't get through our payment processing system. So let's go around again. Prediction. If we try and buy luggage on our website using Firefox, something is going to go wrong. Experiment in this one doesn't even need A/B testing. You grab someone who has Firefox, and you say, hey, can you go and try and buy something on our live website? By the way, when you do this, be sure to use the company credit card, because if you buy something from your own company using your credit card and then try and claim it back on expenses, you create an infinite loop in the tax system, and all the money disappears down it. And they go through, and sure enough, in this scenario, they get to the experimental stage. Analysis, yep. Our credit card provider who we outsource to, they have a new extended validation certificate, and Firefox is not supporting it. Communication. Go on Twitter and complain. Write a blog post. File a support ticket. Tell all the other people in the meeting. Get the fact out there. We have just discovered something that we don't think anyone else knew, because when we looked for it, we couldn't find it, which is that easycard.com doesn't work with Firefox with their new certificate. And you go around again. Except, we've learned something, but we haven't actually fixed the problem. We know what's causing it. We have a much better understanding now of the system that we are dealing with, of the problem that we're trying to solve. But what we have not done is delivered a solution. Now, that is a really important distinction, because when you are doing experiments, there is often this danger that people are going to think that the experiment is actually the product. So here is a website prototype. Have you ever had the experience where you've built a high-fidelity prototype of something, you show it to one of your customers or your clients, and they're like, yeah, that's nice, that's nice, that's nice, click, 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 brilliant, when does it go live? And you say, 3 months from now, and they're like, what do you mean, this looks finished? And you say, this is not finished. This is a prototype. This is an experiment. We just built this to put in front of people to make sure that our designs were valid. And as far as they can see from some basic interactions and a sort of very high-level assessment of what the thing looks like, it's not an experiment. It's finished. It looks real. There are two things we can do to work around this. One of them is, if you are doing experiments, make them look like experiments. There is a prototyping tool that I use which is called Axure, and I love Axure because it literally has a little slider on one of the screens called sketchiness. You can build a high-fidelity prototype, and then you can go, right, make this 50% sketchy, like, back of a napkin, take all the colors out, turn all the images into placeholders, put in the lovely, awesome handwriting font, and then publish that to the intranet so I can go and show it off in a meeting. And people go, oh, yeah, this is... And at that point, the bit of their brain that thinks this is finished and shiny doesn't even kick in. They're going, okay, so we're just looking at gray boxes here. Can I work out what the boxes do? So don't be afraid to do this. If you're doing sprint planning and you have something which is unknown, it's often a pattern. Someone's like, how long is it going to take? You're like, inside you're thinking, well, we don't know, but we think it'll probably take 2 days to find out how it works, and then probably another 2 to fix it. So you'll say, yeah, 4 days, say end of the week. Why not say to them, I tell you what, why don't you give us 2 days to investigate? And then we'll get back together on Wednesday, and we can tell you, maybe our investigation was successful. Maybe our investigation is just, this is a massive can of worms, and we genuinely have no idea. But we are going to take 2 days, and we're actually going to, at the place where I work, we put tickets in, which are investigation tickets, with acceptance criteria of, we understand this, someone has written it up, it's on the wiki, and we're not starting in the dark when we actually come to implement this thing. And it's quite a useful technique for getting people to buy into it, especially if you can involve them in the process of designing the experiment. You sort of, well, what do you want to see? What do you think is going to happen? If you're doing experiments, make them experiments. The other thing that you can do, which is a sort of slightly more controversial approach, so this is Fred Brooks' Mythical Man Month. It's a great book about computer science. The language in it is sexist as hell because it refers to all engineers as men. But apart from that, it has some fairly sort of interesting points in it. And he makes a great point in this. He's talking about something called a pilot system. And the exact quote he says is, the management question is not whether to build a pilot system and throw it away. You will do that. The only question is whether you plan in advance to build a throwaway, or you promise to deliver the throwaway to your customers. The first version of whatever you build is not going to be right. It will be the wrong product, or it will be the right product and it doesn't work properly. It will have defects, because you will learn so much about the problem you're trying to solve in the process of solving it that your initial ideas will mostly turn out to be wrong. And so, in the 1960s, when this was written, Fred Brooks is writing in a decade that built Apollo and the Boeing 747, big engineering where you can't really fail fast and cheap, because spacecraft and airliners don't fail cheap, ever. They do fail fast, but that's not really the point. But, in modern software, we have continuous delivery and application updates, and lots of stuff is online and cloud-based. We have a whole different idea, which is we can actually engage the customers, and we can say, we're going to do an experiment, and we actually want you to be in it. We're going to ship something very, very small. We're going to ship something that the MVP, the minimum viable product, actually, the thing I like to call it is the MLP, the minimum lovable product. Often the smallest thing that's viable isn't actually going to get people necessarily engaged with it. But you make those stakeholders, your customers, part of that process. You say, it is an experiment, and we may end up throwing it away, but we want you to help us refine that approach. And the trade-off you get, the benefit of doing that, is you get to do it very, very quickly. Now, there is an old joke. René Descartes goes into a restaurant, and at the end of dinner, the waiter says, would you like anything else? He says, I'd like a cup of coffee without cream. The waiter goes to the kitchen. He comes back a few minutes later. He says, I'm very sorry, Monsieur Descartes. The kitchen has run out of cream. Would you like coffee without milk? There's another version, which is where René Descartes is working as an Agile consultant. And he's with a client, and they're talking about their planning process. And he says to them, the Agile Manifesto says that we should respond to change over following a plan. And the customer says to him, oh, that's brilliant. We don't have a plan. And Descartes says, that's crazy. If you don't have a plan, how can you choose not to follow it? It's the illusion of choice. There are organizations who think that Agile is great because it means that you can throw away your ideas about what you're doing. It is important to have a plan. It is important to have a vision, which is This never happens, but the vision is what you are going to do if you don't learn anything new and if nothing changes. Now, there's a trap that a lot of organizations fall into where you have a vision, say, that looks like this. Across the top, we have business features, requirements. Down the left, we have technical requirements, layers, processes, steps of implementation. There is a very old school way of approaching software where you say, right, this is our vision, this is our design. First, we are going to design the architecture for all of it. Once we've got that, we will build the data layer. As soon as we have the data layer, then the business logic can be implemented easily. Once we have business logic, we'll put a user interface on it. Then we will launch it. Then we will get feedback. Now, this feedback will be in the form of hundreds of people saying nasty things about your new product on Twitter, and phoning help desk, and filing bugs, and generally saying, you built this thing that doesn't work, and nothing works the way it's supposed to, and what have you been doing for the last 6 months? And probably eventually someone will go, look, we're getting really fed up of getting phone calls all the time because the thing we thought we fixed is broken. Could we please put some monitoring on this so at least we know about it before the phone starts to ring? What if you did it this way? Pick a feature, one thing that is actually useful, and ship that all the way to production. Instead of getting hundreds of nasty tweets, you'll get tens, maybe 5, maybe none if it's small enough and you've got the people involved so that they know that you're still knocking the edges off. Talk to them, see what it is that they want next. Brilliant. They want that. Now, based on that, you realize that your original vision was wrong, and actually the next thing is not necessarily to go A, B, C, D, E. You're going to jump and you're going to ship this thing next. And at every stage, you are making sure each iteration of this, each experiment, you are picking the smallest thing that can work, you are shipping it, you are communicating, you are analyzing data, you are going back to the observation stage, and you're feeding that back into the next iteration of your product. Because what you probably find is that you can do D and E, and C, actually it turns out you never needed that at all. You had this entire piece of your vision, your product vision, that through repeated experiments you determined that the hypothesis that said it was necessary has turned out to be false. The point about these experiments, the data, the analysis that happens when you're doing agile product development, you can't get that without talking to the people who are actually using it. And a lot of old school project management techniques have a sort of, Gantt chart. We'll do a design phase, then we'll do the implementation phase, then we'll do a testing phase. When we finish testing it, we'll launch it, and we'll have a bit of time at the end to fix the bugs. This never works. This never ever works, because the things you learn at this stage, you really wanted to find out when you were over here. Now, this is anecdotal, but based on my experience, if you're doing a piece of development, take the time from officially starting it to the time when a real customer first gets their hands on it. At the very earliest, that is going to be halfway. If you're 8 months into a project and you haven't shipped anything yet, you're going to be at least another 8 months. If you are 2 years into a project that you're confident is going to be a 2-year project, it's not. It's going to be a 4-year project unless someone's already using it. And that's a lower bound, It gets worse. You could be 3 months into what you think is a 6-month project. It's actually going to go on for 3 or 4 years. Or it's going to get cancelled because the costs spiral. And I think in all of these cases, this is because you cannot do this experimental, you cannot apply this scientific method without getting valid data to inform your observations and your next round of hypotheses. And you can't do that until you've shipped. Okay. So to wrap up this afternoon, I'm going to show you some statements. Things that people in our industry say, and then go on and do things as though they were true. And between us, I want to have a bit of a talk about how would you actually design a scientific experiment to validate whether these hypotheses were true or not. So someone says to you, not my code, it must be a problem in the database. Something which happens quite a lot. Experiment. How would you turn this hypothesis into a prediction, and how would you then test that prediction experimentally? Open the debugger, see if the code is behaving correctly. That would be one way of doing it. What would that tell you?
It would tell you if it was his code, then...
Do you want to grab the mic, sir?
It would tell you if it was his code, then you would see the code behaving incorrectly in the debugger, and if it wasn't, you know it could at least be a problem in the database.
Okay.
Not necessarily, but...
So we have a prediction there that if you look at the code in the debugger, then If it's not their code, the debugger will show no problems, and you can validate it's the database. Is there another way you could approach it? So we got two components here, and we're trying to determine scientifically which one of them contains a defect. Isolation test. Run the database on its own. The prediction there, well, if it's a problem in the database, then the database will still exhibit the problem, even if your code isn't involved. So we'll go and we'll run this thing in isolation. We had this very thing went round and round and round in my team for a long, long time a few years ago. We were using nhibernate, which is an ORM for .NET, which was very, very popular about, I don't know, 5 years ago. And we had literally a bunch of queries. The code looked fine. The data looked fine. When you put them together, it didn't work. And it went backwards and forwards. Developers saying the code is absolutely fine. It must be the database. We took the queries, and literally we'd copy and paste the query from the debugger into the database, and it would work perfectly. And then you'd put it back. And it turned out that the reason why none of this was working was nhibernate was passing everything as a Unicode string, and all of our indexes were on ANSI strings. And that doesn't show up in any of the debuggers. That took a long time to get through. But that was literally breaking it down into these little steps. Right, if we try X, we think Y is going to happen. And eventually it came down to, if we specify one of these parameters as a .NET string and run the code in isolation, is it still going to exhibit the problem? And it did. It's like, right, that's taught us something. Let's move on to another statement. Dependency injection makes everything impure. Is this true? So this was from Mark Siemens' talk yesterday. He's talking about Haskell and functional programming and stuff. And this went on Twitter, and several people shared it. Clearly they think there's some wisdom here. Do we think it's true? Could you design an experiment to test it? Yes.
You don't need an experiment. You can mathematically prove it.
This is not maths, this is science. There will be experiments. How would you prove it?
Well, you would build a simple mathematical model of a programming language where you have effects. You can take lambda calculus if you wish.
Yep.
And then you will write a formalism of what is a dependency injection, and you'll write a proof that says, if I use this, then this is where effects are happening, and therefore it's not pure.
I guess the question then is, how do you formalize dependency injection, given that everyone disagrees on what it is to start with?
That's exactly the point I was coming on to, is we have this word in here, impure, and we also have dependency injection. I think there is now a reasonable degree of consensus in our industry about what dependency injection is. But purity is one of those words, like better or faster or more efficient, which you need to understand. All the people who are trying to evaluate the truth of this statement need to agree on what pure and impure means in the context of developing software systems. Because until you actually understand what it is you're trying to test, how do what are you hoping to learn from conducting the experiment? Object-oriented development means your code can easily be reused in other programs. Who in here is or has been an OO developer? Who's still an OO developer? Is object-oriented development better than what you were using before? Does it allow code to be reused more easily in other programs? Could you design an experiment? And if so, how would you conduct it? So we have this word in here, easily. What is ease in this context? How would you be scientifically rigorous about your definition of ease of code reuse? So spin up two teams. This is one of those interesting experiments you get in fields like sociology, where they're like, we're actually going to do things with two big sample groups. And although a lot of sociological and psychological research follows the sort of observation hypothesis approach, it's often very difficult to reproduce their experiments because you can't get enough experimental subjects because you don't have enough funding. But you could potentially do this. You could get two software teams, and you could say, right, your team are going to use any object-oriented paradigm you like, Java, C#, C++. You are going to do everything procedural. And just for fun, you're going to have another thing. You're going to use Haskell. You're going to do everything pure functional. And then you would need to come up with some objective metric about ease of code reuse. Now, a good idea there would be cyclomatic complexity of the systems that they're actually building. If you've got easy code reuse, it makes sense that most of your use cases and your features will actually end up flowing through the same elements of your code, the same discrete function points and things. So you could potentially do an analysis of a code base, and then you say to the developers, well, how easy was it to get it to do that? How long did it take? How many hours have you spent working on this? It's interesting, you take these statements, which often, entire massive teams of hundreds of people have dumped C for C++ because they believed this statement to be true, without ever actually going, what are we expecting to see? What's the hypothesis we're predicting here? Because often, experiments, there are entire companies out there where the company is actually a hypothesis that they're hoping will pay off. If we build an app that lets people summon cabs using their smartphone, it'll get used, and it'll be successful. Good hypothesis, that one worked. If we post people a little plastic cat that lets them scan barcodes in magazines to go to web addresses, that was a hypothesis that didn't work, which is why everyone's heard of Uber and no one's heard of the QCat. Often startups are these little ideas that they think, if this is true, and then they bet an entire company on it, and you think, could you have done something smaller? Could there be an experimental way of validating this? Developers who attend conferences write better code than developers who don't. Experimental validation required? Exactly. How do you quantify better? Is it code that has more shiny things in it? It is code that's easier to read? Is it code that runs faster? Is it code that has a lower total cost of ownership over the course of 5 or 10 years? A lot of people use this, I need to go to conferences, so I'll be a better developer. That's like, okay, well, you'll probably be a happier developer. Is that necessarily the same thing? I'd love to see an analysis of this one. Our team will be more productive if we have daily stand-up meetings. Again, we have this weasel word, more productive. Unless you're tracking 2 teams of identical people trying to hit identical targets using one of them's doing stand-ups, the other one isn't, it's very hard to get the experimental data that'll back this up. Ruby's better than PHP. You'll notice a pattern in these. An awful lot of the things that people use in software to inform the decisions we make have these words: easily, better, more efficient, faster. It's all comparative. It's very seldom is there an objective. We predict that the following thing is going to happen. We use these sort of fairly nebulous terms. And it's interesting trying to break those down and think, well, what do you actually mean by better in this context? The most efficient and effective method of conveying information to and within a development team is face-to-face conversation. This is one of the assumptions, the principles underlying the Agile Manifesto. I know some teams who swear by it. I know some teams who are like, that's completely wrong and it's optimizing for all of the wrong things. Again, do you think you could experimentally verify this? Depends what you're optimizing for. What is an efficient method? Conveying information to and within a development team who are all in the same room at the same time, sure. If the development team are not in the same room, or they are in the same room but they're not in the same room at the same time, the people who are working different shifts, the people who are working on a different time zone, they have no access to the content of that face-to-face conversation. Is that efficient or effective? Depends on the team. It depends on what you're optimizing for. Okay, that's pretty much it from me today. We have a few minutes for questions, if anybody has any questions. Or on the other hand, if everyone has achieved total enlightenment. Yes?
So I think one of the interesting sort of things we could see at the end was that in physics, when people say things, it's like fairly clear to figure out what do they mean by it.
Yes.
And if we were to use scientific method for programming, we would need some clear things to sort of claim as well.
Yeah.
And it looked like none of the sort of things you were showing in the end were particularly scientific because they didn't make any clear claims. So do you think do you think those are just things that people shouldn't be saying at all? Or do you think there are some other good things that they should be saying instead?
Those are things that in most cases I deliberately chose because a lot of people would agree with them, but it is very, very difficult to kind of take a rigorous approach on determining whether they're true or not. There are lots of things you can say in software. I mentioned an example earlier with a database index. I think if I add this index, SQL Server will do this for you. It'll go, if you put this index on this table, you will see a 99.6% improvement in the performance of this query. And you can test that. And most of the time, it's pretty close. You can, in many cases, you're working with, okay, we have a latency of 500 milliseconds talking to a remote service. If we reduce the number of remote service calls from 20 calls to 5, the total latency of our user interface will drop from 10 seconds to 2.5 seconds. These kinds of predictions are not terribly controversial because, as you say, they are more akin to physics and other sort of forms of more mathematically rooted science. But we make fairly big and fairly expensive and significant decisions based on things that we think are true. And it's interesting to me to look at these and think, well, how do you actually break that down? What do you reduce it to? Any other questions? Great. In that case, thank you very much. I would ask for your help in verifying one more piece of experimental data. I have a hypothesis that people who give green feedback will go on to live long and happy lives. If you'd like to be part of this experiment, it's very easy. You put in a green card and then go and live happy ever after. If it doesn't work out, let me know.
I think we need to split us into 2 groups. Half of the people put green, half red, and then you evaluate when we...
Yeah, but then I'd need to all get you back in 10 years, and then we'd be trying to measure happiness scientifically, and only the Danes can do that.
We're just trying to bring the green portion down so you also affect that. Of course.
Anyway, thank you all very much for coming. Enjoy the rest of the conference. Enjoy the party tonight. I'll see you around. Thank you.